So today we will talk about spray combustion. This is actually like a follow up to the droplet combustion that we did, where we were basically considering only a single droplet at a time, and at the time I pointed out that it may or may not be exactly the way it happens in reality, because in reality you may have a cloud of droplets that burn, or you may have all the droplets evaporate by the time they reach a gas phase flame, and therefore you do not necessarily have a droplet combustion and so on. So there are lots of different possibilities, and it also depends on whether the spray is dense or dilute, and typically we think about a single droplet combustion mode in a spray. In reality most of the droplet combustion happens only in sprays, right. So spray is the more realistic situation that we need to think about, and the single droplet combustion mode probably happens only in situations where you have dilute sprays and so on. So let us now see if we can take the idea of the single droplet combustion further and see when that happens in a spray. So basically we will now look at spray combustion. There are a couple of ways by which you can think about spray combustion, similar to the way we have been dealing with the gas phase flames. So in the case of gas phase flames, we had on the one hand premix flames, on the other hand we had the diffusion flames, right. So we could think about these things as we could still think about like analogies to spray combustion similarly, but however we have to think about, in reality it's again in between. It is not, it's neither premix nor diffusion. So what is really meant by a premixed spray combustion, or what is meant by a diffusion flame kind of spray combustion? On the one hand you could now think about droplets that are now laden in an oxidizing gaseous flow, gaseous oxidizing flow. So if it is possible for us to mix liquid droplets of fuel in a gaseous oxidizing flow, and of course the gaseous oxidizing flow could also have inert gases, like for example if you are looking at a gasoline air mixture or something like that, right. So air has the oxidizing gaseous species as well as inert gaseous species, and then you are now throwing in liquid droplets of gasoline, and then let us suppose that you now have that flow up here, flow in a tube, and then you now stabilize the flame in between. Or you could also think about more like a Bunsen burner, where you have the approach flow is actually made of a mixture of liquid droplets in a gaseous oxidizing flow. So that is one configuration that you can think about. On the other hand, let us suppose that you now just have an orifice through which you just issue a liquid fuel, and because the orifice is so small, or the pressure injection pressure is high, or a combination of both, you now have a spray that is coming out. So what's basically coming out is essentially a liquid fuel spray, and the oxygen has to get in, the oxidizer is in the ambience, and it has to get entrained into this, and as it gets entrained it mixes, vaporizes the liquid, and burns the liquid fuel and so on. So that would be like a diffusion flame counterpart. In reality, as I said, you would have a combination of these two things. It's neither this nor that, and of course you can think about like a partially premixed flame that is established in what could be nominally a non-premixed injection of liquid fuel, but since you have like a standoff distance, it allows for some mixing and so on. So many such possibilities exist in reality. So what we will first consider is a premixed mixture, for the sake of simplicity. Mixture of liquid fuel droplets and oxidizing gaseous oxidizer plus inert or diluent, right. So as I said, you could have like a possibilities, or let's say you have a tube and then you have now the reactants, and then you have a flame, and then you have products. Or you could have a burner in which you now send the reactants, and then you have a flame, and then of course you have products downstream of the flame. So these are different possibilities. So in this case, for example, you now can talk about a SL, and what is really opposing it is the normal component of the flow, right? So that is equivalent to saying you now have a reactant flow at the speed of SL that is approaching a stationary flame, or in a flame fixed coordinate system. So in this case what we are basically talking about is, let us suppose that if you now look at this locally, or in this region, what this basically amounts to is, if you now have a flame, right, what you are essentially saying is you now have a droplet that is approaching the flame along with oxidizing gas with inert, and then it begins to evaporate, because it is now in the influence of the flame as far as the heating is concerned. And as the heating happens, you now as the evaporating happens, it now the fuel vapor is now evaporating out and then also flowing along with the oxidizing gas and mixes, and you now reach the flame. And when this liquid droplet goes past it, you now still have a liquid droplet with a flame behind around it as an envelope flame, and this now decreases further into a smaller droplet and then flame and so on. So this is typically the kind of picture that we are looking at in these situations. Alright, so if it's possible for us to now set up something like a Bunsen burner with liquid fuel droplets, we should now expect the larger ones particularly, and that's what I'm just next going to talk about. The larger ones will actually get start burning as they flow through the flame, and then begin to go as individual droplets that are burning like in single droplet combustion that we have seen, but the smaller ones will now have evaporated by the time they reach the flame. Therefore you won't have a single droplet combustion, right? So the question that we have to ask is, what is the limiting droplet size below which you will not have a single droplet combustion mode? Okay, so if this droplet is going to actually shrink to 0 size by the time it reaches the flame, that means its starting size should have been small enough. If it is large, then it keeps on shrinking, but when it gets past, it begins to burn in a single droplet mode, right? So the question basically is, what is the limiting size below which the droplets don't burn in a single droplet mode? The answer to that question can be done by a simple analysis. So the thing that we look at is, what is the residence time of the droplet in the flame, right? So so what we are basically saying is sufficiently small droplets are completely vaporized, in the preheat zone. The preheat zone of the flame is where the heat conduction is happening. So the characteristic time of traversing through the preheat zone is let's say tau d is LD, which is like the flame thickness divided by SL, and that would be K divided by Cp rho g divided by, we should have actually LD is K divided by Cp rho g SL, then we also have another SL, therefore you get a SL squared, and then what we have to compare this time is with the droplet evaporation time. How long does it take for the droplet to evaporate versus how long is it going to be within the preheat zone, right? So the droplet vaporization time is tau v is dl naught square divided by 4k, that's essentially talking about the radius divided by the in terms of surface area divided by the evaporation constant. It's essentially coming from the d squared law, and so this is as if this is d squared law for evaporation. We are not basically saying that it's going to burn in a single droplet mode, but we talked about when we did single droplets, we also said that the same approach can hold good for evaporation. So then we use the expression for the evaporation constant that we had obtained to get natural logarithm 1 plus b, where b is in our case Cp T infinity minus Tb, the boiling point divided by the latent heat of vaporization. So if you now say that these two times are comparable, then we begin to get a diameter of the droplet below which you won't have a single droplet combustion. That means you won't have anything that's burning and coming out of the flame, right? So for tau d approximately equal to tau v, or the same order, dl naught min squared equals 8 rho g by rho l k over Cp divided by rho g SL the whole squared natural logarithm 1 plus b. The reason why we write rho g SL together is this is actually the mass burning rate or the burning mass flux. Okay, so now for typical values of things like if you now assume approximately stoichiometric mixture for the fuel and air where the combustion happens, and then you now throw in like rho L over rho G is of the order of 1000 and then and so on. So you do all these things, then so this gives about 10 microns. So dl minimum dl naught, that is the original droplet size, the minimum original droplet size is of the order of 10 microns, 10 micrometers for typical values. For other quantities, right? Now we can also see the dependency here. So for rho g SL squared of the going as p to the n, it's coming from how the burning velocity depends on the pressure, and we are looking at rho g SL the whole squared. So we remember that, and we say it's going as p to the n, then dl naught minimum squared goes as p to the 1 minus n, right? And this is purely coming, so what this means is the pressure dependence purely comes from the preheat zone length, okay, and we don't have to worry about the dependence of the evaporation time on the pressure. So the evaporation time is not dependent on pressure, it's only the preheat zone length that changes with pressure, and therefore the residence time of the droplet within the preheat zone is going to change like this, right? So that's mainly the effect of pressure. What we should actually look for, and we now have these bunch of droplets here, so the picture that we drew is only for one droplet, right? But that's not reality. So this is assuming like a dilute spray essentially, and then talking about a single droplet combustion event in the case of droplets of size larger than the d minimum, right? So question is, what is the interaction effect? Okay, so the droplet interaction now assume for this purpose equal size of droplets, right? Then what we are essentially saying is, let us suppose that these droplets are located in space at a particular time with some distance, and what we would like to think is the distances are about the same, okay, for the sake of what we are doing, not very difficult. We are basically looking for something like an average interdroplet distance. So what we could then do is now draw spheres around these, right, and so on. And if you now say this is the sphere around which around the droplet that you have drawn is having a diameter that's approximately equal to the interdroplet distance, okay. And then if you now take that sphere worth of mass of oxidizer, neglecting the presence of the droplet, okay, and then take the mass of the droplet, you can now form a fuel air mixture based on that. Alright, now there are voids here, and those volumes of the oxidizer we are not considering, so it kind of compensates between taking this volume and not taking that volume, right. So approximately speaking, the fuel air ratio is F over A is approximately 1 over 6 pi dl cubed rho L. It's essentially 4 over 3 pi RL cubed, but dl is RL divided by 2, sorry, RL is dl divided by 2, so if you now plug that in there, you get the 1 over 6 dg cubed rho g. So the dg that we are talking about is the interdroplet distance average, okay. So dg average interdroplet distance, right. So what does that mean? This is like rho L over rho g times dl over dg the whole cubed. So what this means is, of course, if you are for nearly stoichiometric mixture, stoichiometric combustion, for typical hydrocarbons, let's say typical liquid hydrocarbons, your F over A should be around 0.05. Alright, you can evaluate that for typical, so you look at the stoichiometric chemical reaction, and that means it's balanced, and then you can look at the mass ratios for that. If you now plug that in, and rho L over rho G is about 10 to the 3, right, then we can find that dg over dl is of the order of 25, right. So 25 is like more than 10, so we can say that the interdroplet distance is quite larger when compared to the droplet diameter itself. So this doesn't mean too much interaction. But if you now start thinking about the effective pressure, okay, so at higher pressures, rho g increases, okay, because as pressure increases, rho g increases. So if rho L over rho g, so if rho g increases, rho L over rho g decreases. If rho L over rho g decreases, then dl over dg will increase, or dg will decrease effectively, right. So dg over dl then dl decreases. For example, in automobile engines, if you now look at the typical kind of pressures, you will find that those pressures dg by dl would be as lower, like about 15 or something, okay, still around greater than 10, but you are now hitting a limit where you have to consider the interactions. What we should then start to think about is, we started looking at a premix mixture, but let's now look at a jet a spray jet and a spray jet flame. So this is now getting closer to reality. So what's going on here is two things. One, as you now have a jet that is coming out, this is jet of liquid fuel, it's also beginning to entrain air, and then of course we have ignited it, and there is a flame. The question is, are we having individual droplets that are burning in this flame, or is it like an envelope of all the droplets that is burning together? That's essentially the question that we have to ask, right? So the answer to that is, of course the droplets are evaporating from the heat of the flames, right? So the competition now is between how much is the entrainment, right, because you need the oxidizer for the flame to happen, and so therefore you need to have the entrainment to happen. So how fast is the entrainment versus how fast is the evaporation? So the evaporation is going to give rise to the fuel, the gaseous fuel. The entrainment is going to bring in the gaseous oxidizer, and you need to have both of these for the combustion to happen, right? So typically when you are now looking at entrainment, the entrainment is happening from the sides, and then it starts penetrating to the core. So there is a core of liquid which doesn't see the ambient air significantly, right, for some distance beyond which the ambience penetrates. So you could now think about the inner droplets not exactly going through a single droplet combustion, right, whereas the outer droplets are going through this because there is access to air. So effectively fuel is sprayed and air entrains, right. So droplet at the core, droplets at the core may have insufficient oxidizing ambience. Now, so what you have to look at is the competition between entrainment and evaporation, right. So if entrainment is fast and or okay, it's a combination, vaporization slow, right. So entrainment is faster, vaporization is slower, then what do we expect? Air is now beginning to get available to most droplets, and therefore most droplets can burn by themselves. They are harder to evaporate, therefore they are going to be waiting for the flame to come near them, okay, oxidizer to come near them and the flame to happen near them. So this actually leads to single droplet burning, more towards single droplet or droplet burning singly or in groups, right. Now once you have a single droplet mode of combustion that is established, then it is difficult for the flame to coagulate and then have an outer envelope flame, because once you have the flame you don't have fuel penetrating outside of the flame. So the oxidizer has to come to this to the flame in order to consume the fuel, right. So once you have this mode of burning, this persists. It's kind of like a stable solution that the system approaches. On the other hand, if entrainment is slow, right, and or vaporization fast, so this now leads to a flame that is actually enveloping a what's called like a spray sheet. So now you can look at a spray, you now have a cover around this, and that's exactly where you expect the flame to happen. So this is envelope flame at the spray sheet, right. Now once you have a envelope flame, then that is not going to let the oxidizer get in, okay. So the droplets will now be waiting for the oxidizer, but no oxidizer is coming because it's all getting consumed in this flame, so they just begin to get evaporated because of the heat from this flame, and they will have to continue to undergo combustion in the envelope flame. So once you have an envelope combustion mode, it sets in and it persists. It is hard for it to transition into a droplet combustion mode, right. So this persists. Now typical examples of these are, for example, if you are now looking at a situation where the vaporization is slow, that means we have to look for materials that are less volatile, okay. So typical example of this would be even solids. For example, you look at coal particles, okay. So if you now look at pulverized coal, so coal or coal dust, okay, example, coal dust flame. Now the example of this would be the second one, where the evaporation is fast, is essentially oils. So oil flame, right, where the oil is typically quite volatile, and so the oxidizer spreads, the gaseous fuel spreads out and meets the oxidizer even before it can entrain significantly. So then what we have to look for is how does this, what we call as a cloud combustion or a dense spray combustion happen, okay. We define something called a group combustion number, or you can call it a group combustion index or number. This would be called G, and this is defined as N, capital N dl naught divided by L, where N is the total number of droplets, total number of droplets that can be now written as I should say goes as NL cubed, where N is the number density, that means number of droplets per unit volume, and L is characteristic dimension. Right. So essentially what we are saying is, if you now have a total number of droplets times the diameter divided by the characteristic dimensions. Let's say, for example, if you are looking at a spray flame or a swirl flame where you are sending in the liquid in a swirl flow and so on, you have like a burner diameter. So within this burner diameter, or of the order of the burner diameter, how many droplets can you space is essentially what is indicative of the group combustion number. And what it basically means is, if you have a large G, it indicates a group combustion. If you have a small g, it indicates single droplet combustion. Group combustion, and small g single droplet combustion. Now in reality you could have also things that are in between. That means you have small clouds of droplets that are burning with a flame enveloping it, but many such clouds separately, right, as opposed to when you say group combustion, it's like all droplets that are there are having a single flame. So there is a reality that's in between. So it's like these are extreme cases, right. So and then the other thing that you have to point out is, this is purely a geometric parameter, right. So we are talking about what's like the spacing between the droplets, if you will. So G is purely a geometric parameter, and it doesn't take into account these things. Like, we are not looking at how well is the entrainment happening versus how well the vaporization is happening, okay. So these two, we'll keep this in mind. But before we proceed with taking into account those in a spray jet flame, but what we will think about is it possible for us to think about like a spherical cloud of droplets, right? What could happen if you now have a spherical cloud of droplets as a function of g? So if you now start from a large g towards a small g, what happens to a spherical cloud of droplets? Now there are 4 possibilities that can happen with a spherical cloud of, so consider a spherical cloud of droplets, right. So what we are basically saying is, can we have a large G situation where we are looking at a group combustion, and what that means is you now have lots of droplets that are in the core, and they are non-evaporating, right. So if you now have like a slow vaporization situation, okay, then let us suppose that you now have a spherical boundary, imaginary boundary, imaginary spherical boundary of non-evaporating, non-vaporizing droplets, and out of which you now have let us say smaller ones which are evaporating droplets. So they are obviously much smaller, and I am just representing them by a dot, and you can now talk about this as the spray boundary. So in all the pictures that I am going to draw for the 4 possibilities, the broken line refers to what is called as a spray boundary, okay. So there is another way of thinking about this. You can look at like a spray that is coming out of the board, right, in a cylindrical manner. It does not have to be spherical, but you can look at things happening in a circular manner as a cross section, right. So it is like you now have a non-evaporating core and a evaporating surrounding that forms the spray. So this is the broken line basically means this the spray boundary. So this is vaporizing droplets, and the broken line is the spray boundary, and you now have the actual flame around this, right. Now as you now increase your decrease your G, as you now go in this direction of decreasing G, the other possibility is you do not have a core of any non-vaporizing droplets. That means this diameter basically shrinks to 0. You are now beginning to think about droplets that can vaporize faster, but still not fast enough for flame to eat in, okay. So you now have a single spray boundary without having to distinguish between vaporizing and non-vaporizing droplets, because all of them are vaporizing. So that is vaporizing droplets, and then you have a flame around, right. Now the next possibility is for the flame to move in, okay, into the spray. So as I said, the broken line is the spray boundary. So the moment the flame moves into the spray boundary, you now begin to have single droplets in the periphery, single droplet burning in the periphery, and then you have group combustion in the middle. So that gets us to a situation where let us suppose that you now have this picture of vaporizing droplets in the middle, and still it is not the spray boundary. You actually have the main flame. Now we have to distinguish between main flame and individual droplet flamelets for those that are burning outside this. So those are individual droplet burning, right. And this is what constitutes your spray boundary. And finally the flame now eats into each and every droplet there, okay. So that means you now have a spray boundary in which all droplets are burning individually, and so on, right. So this is a limit of low G, and this is individual burning, and this is now low G, right. The question is what happens. So this is as if like you had these droplets kind of put together in isolation as if they were not part of a flow, right, and then we were beginning to play with the G. So if there is a high G, then there is more group interaction. When there is low G, there is less group interaction, you have more individual droplet burning, and so on. But what happens in reality for something like a spray jet flame? The answer is, in a spray jet flame you now have a flow field with a variable G. So you start with something like a very dense spray that is just beginning to atomize and then spread out, and then you now have more and more entrainment that allows for individual droplet burning further out. So it's like a variable G that starts with a high value and then keeps proceeding along a low value. So this is where it's not just purely a geometric parameter that we can rely on, we have to bring in the flow effects. Therefore in a spray jet flame G is variable, right. So you now get into a situation where, let's suppose this is a center line, and let's say you had lip of the nozzle and which issues out this spray, and you can now think about like a potential core, and you now have near the center line you have bigger droplets, but away from the center line let's say you have smaller droplets because they are evaporating, and now you have the main flame or the internal group combustion flame right, and outside of which as you now keep going the G actually decreases and you now have lots of cloud combustion going on, right, forming the spray boundary. So this is like the, or maybe keeping with the convention we should use broken line. Spray boundary, and this is multi-droplet combustion, and there is a overall turbulent flame brush that we will have that encompasses the entire flame, and so that's essentially a turbulent flame brush. We might look at it when we do turbulent flames. That is, it's an envelope of all the fluctuators, right? So that's the turbulent flame brush. How do you formulate this kind of problem, right? So the way we have to do it is obviously to deal with it in a statistical manner. So we have to look at how to do spray statistics. spray statistics, what you do is you now have what's called the spray distribution function. Function f of r or L, which is the droplet diameter, position x, velocity u vector, and time, such that this is like a density distribution. That means f of RL u x, should say x first, u and t, drl dx vector du vector. So this is basically a 7-dimensional space in 3D, right? So you have 3 components of velocity and 3 directions of location, and then the radius. So this quantity now, right, indicates the number of droplets of radius between or let's say in range RL to RL plus DRL, velocity position in range x to x plus dx, that is within this bin, and velocity in range u to u plus du, right, at any time t. It is time dependent, all right, so we have to now let this fluctuate in time. So when we now use the word RL, sorry, the quantity RL, we are implicitly assuming a spherical symmetry. So zoomed. There are ways in which we can relax this, but we have to see when this is relaxable. So now typically small droplets, for example, if you're looking at things like 10 microns and so on, 10 to 100 microns, like say look at that range, for most typical fuels you have a significant surface tension effect that spheroidizes the droplet. Okay, so the sphericity is maintained because of the surface tension. Therefore we have to actually look at what else is causing the droplet to be non-spherical as competing against the surface tension. So what typically allows for the droplet to be non-spherical is when it now tries to flow, you now have a shear that's happening at the surface, as well as a hydrodynamic instability, because you now have high density and low density interface which becomes unstable and so on. These things are obviously proportional to the relative velocity between the two, the droplet and the surroundings. Okay, so if the droplet were to be stationary, you don't have these effects, right? So therefore the Weber number describes the effect of surface tension relative to that of the dynamic force on the droplet. So WE, that's a symbol for Weber number, is 2RL, that's for the diameter, gaseous density times modulus of u vector minus v vector the whole squared, that's the relative velocity between the droplet and the ambient gas, divided by sigma, which is the surface tension. Right. So u is the droplet velocity, v is the gas velocity, right. Now for WE greater than or equal to about 20, droplets tend to deform and break up. So if you are looking at atomization situation, you are looking forward to deformation of liquid sheets into ligaments and ligaments to droplets. So you are looking at a high Weber number situation, okay, but once you get to fairly small droplets, the Weber number becomes small and then the surface tension takes over. So for a Weber number greater than 20, droplets tend to deform and break up, right. So given this, we can now write what's called the spray equation for F on how this is actually going to go. Spray equation is a dynamic equation for F RL dot F plus now a divergence with respect to x of the droplet velocity carrying the F and a dynamic divergence with respect to u of the body force all equal to a S, where now we will now explain these terms. RL dot is something that we are familiar with, which is dRL over dt, right. So this basically tells how this F is going to change because you are having a evaporation or burning that changes the R at a certain rate with respect to time. And for example, if d squared law holds, right, we know that RL dot is goes as 1 over RL, right. That's something that we have seen before. G is, as I said, the force per unit mass. Whatever forces are acting that change the droplet, the spray distribution function. And S is actually the most important thing and also the most difficult thing, is essentially the source term. And essentially you have to look at two sets of quantities. One is creation and destruction. So creation and destruction, so it's essentially a net source term of droplets, right. So creation is like, for example, by atomization, and destruction is by coalescence, and let's say impingement with the wall, right. So wall collision, etc. So it's kind of like what's called the population equation that keeps track of the droplet population given by F, and what you're looking for is how do the droplets get created and destroyed as a source of this that's getting dynamically going in a flow field. Now these are difficult to model, and the fidelity of this equation lies in actually how we model this, and that's where all complexities remain.